Right, welcome everyone. So today I just finished my PhD, so bear with me if my slides look a little bit too much like a PhD defense. But today I'll explain a little bit to you what an event camera is and how we can use it in robotics as well, different computer vision tasks. So the primary goal here is to actually, inspired by natural vision systems, is to emulate these systems in robotics or computer vision systems. These animals have been a powerful inspiration for us researchers because they can do highly agile, very adaptable perception, all while consuming only a fraction of the power that, as for example, the current LLMs or current large convolutional networks are using. So to do this, many people have resorted to using frame-based cameras, so you observe the scene as a sequence of images. However, these images still have a number of fundamental limitations, which is holding back the research field and us attaining biological vision. One of them is motion blur and in a low dynamic range. This means that in certain scenarios, you'll have a lot of motion blur, you'll have saturation effects. This introduces artifacts on your image and actually reduces the performance of downstream algorithms which use them. Another one is latency. So we observe the scene as a sequence of images, but if these images are too far apart, we can actually have significant dead time during which we can't act, and this means that we can actually endanger lives with these sensors. The topic here is going to be about event cameras, which don't suffer from these problems, and I'll explain to you now how an event camera works. So an event camera was first commercialized in 2008 from the University of Zurich from this professor Toby Delbruck. Maybe you already know him. And it's a sensor that is inspired by biological vision. So the idea is that instead of seeing the world as a sequence of images, the event camera only sees changes in the images and encodes these as spikes. So let's consider now this example of a rotating disk, first observed with the standard camera. You can see it's a sequence of images. But now instead with an event camera, it only sees the changes, and this translates the visual signal into a kind of spatiotemporal spiral. You can see that this spiral is very data efficient. You see now there's no motion, so we have no data. It basically captures the scene in a non-redundant way. And also, because we only see changes, we don't have an exposure time, we can actually also capture high-speed motion. We still see the high fidelity of the data structure in the bottom, whereas the standard camera's images are motion blurred. Here on the right, you see a company which produces these event cameras, Spec, which are very small. You can hold them on the tip of your finger. Here's a little bit of a more detailed view of how these events exactly look like. So imagine that we have one pixel over time and it's varying continuously. The event camera will now always look for a specific threshold, which we call the contrast threshold. It's something that you can tune on your camera. And then each time this threshold is reached or under, basically this threshold is exceeded either in a positive or negative direction, we generate an event. And the polarity of the event is basically the sign of the change. And then you can see that these arrows in the bottom, they correspond to the data that we actually measure by the event camera. So it's an asynchronous and sparse stream of data, especially if we now integrate multiple pixels.
So it kind of remembers its previous state that was...
Exactly.
Fired.
Exactly. Yeah, it has a voltage and it always compares it against, and then it resets. Yeah. There's a little bit of a circuit diagram on the top right for you. So now let me show to you some of the application domains where we've used event cameras. Here on the right, you'll see how event cameras have a very high dynamic range. It means that they can see outside of the tunnel and inside of the tunnel at the same time. This is because pixels are independent. They don't have a global exposure time. They also have a very high temporal resolution, which means we can capture high-speed phenomena with low motion blur and with a very high fidelity. And finally, event cameras also have low latency. So the time between a visual stimulus and the data arriving in your camera is very low, which means that we can now install them on high-speed robotic platforms and execute these kind of evasion maneuvers, which are very important. So, So looking at these bottom two pictures, you could ask yourself, why don't we actually just use a high-speed camera? High-speed cameras can also capture the information in a high-speed way. We have a high temporal resolution and low latency. But actually, event cameras also have a very high bandwidth. High-speed cameras, they also have a very high bandwidth, because things that are not moving, you're still taking a bunch of images from them, and this means that you're actually oversampling many of the parts of the image that you don't need to. We could instead use a low frame rate camera to reduce this bandwidth, but then instead we are moving to the right in terms of latency, and this is also undesirable. And we can see that since we have a frame rate, we're basically constrained to this thing which we call the bandwidth latency trade-off. We cannot simultaneously make the data from the sensor low bandwidth and low latency. And this is because we have a frame rate. But instead, because we have an event camera doesn't have a frame rate, we can at the same time have a low bandwidth and a low latency. And this makes them very interesting, especially not only in low latency applications, but in applications where latencies have to change. Maybe long time you don't have to do anything, and then at some point something exciting happens, and then you want to perceive with low latency. However, this comes at a cost, because events now are not captured as images. We cannot process them anymore with vision transformers or CNNs, so we need to redesign some of the algorithms to use this data. Another thing, if you're not yet convinced, is what we term this signal latency constraint. So one of the reasons why event cameras are better than high-speed cameras is because also for high-speed cameras, if you have a very high-speed frame rate, you have very little time to actually expose the images in between. And this means that for a given latency that you want to achieve, you can only achieve a certain signal-to-noise ratio, because we can only expose the image for a certain amount of time. And this means that, for example, for high-speed photography, they often have to use external lighting to make it very bright. This is very power-consuming, and also you need to have active cooling to counteract the power dissipation. And here again, event cameras have a high signal-to-noise ratio, but they still have a low latency. So traditional algorithms work for event cameras have relied on deep neural networks. So what they do is they use these events. You can imagine this kind of sparse cloud. They aggregate them into an image, and then they run a standard CNN on them. And in this case, we can actually see now a few applications. Here we have, Here we have moving object segmentation. So the task is to, as quickly as possible, detect an object in the event stream. Here there's an application to high speed and high dynamic range video reconstruction. So imagine now we're using the sparse events on the left and generating this image on the right. And it's actually quite remarkable that this is even possible. And here I have an example of high speed video that has been generated with images and events combined. And here I'm showing you a fidget spinner which was spun in a black box, recorded with an event camera, and here we can see actually the optical flow that is measured. It's going around in a circle, which is why it has this kind of rainbow color. So these methods are very good, but they're also highly inefficient. Events are sparse, and there's a lot of non-redundancy in the data. But the issue is that when we generate images, now we're actually adding a lot of artificial zeros into the data structure. And this means that they consume quite a lot of power still. So, but the reason why they work so well is because they're using existing networks, existing learning paradigms, and these work very well. So one of the things that has been done is other models, such as, for example, spiking neural networks, have been used to instead process events in a more bio-inspired way. But these models are still difficult to train, and because they don't have mature learning algorithms, and also they often rely on handcrafted or shallow features. So in our case, we're trying to actually reach as close as possible to biological vision systems, which are at the same time robust and efficient, and even go beyond them. So let me explain to you why deep neural networks are that efficient. So imagine that you have this sparse stream of events, my colleague throwing a water balloon to the ground and it exploding. You can get this very high temporal resolution data, but now this data is not directly it's not directly compatible with a deep convolutional neural network. So for this reason, the data first has to be cut into time windows, then aggregated into an image. So you see this kind of frame on the right, and then input to the neural network. And if you have images, sometimes images and events are combined, then these images are additionally used to synchronize the data stream and then merged. So we see that from this data structure, we can still get the low motion blur and the high dynamic range information from events, but we're losing the high temporal resolution and the low bandwidth because we are actually synchronizing the events now into independent windows. And this is because of these blocks here. So now let's have a closer look at these blocks. Normally, the way that an event, a set of events is converted into a frame is with a set of hyperparameters. It's kind of a function that takes events, generates an output. And there's been a few of them in literature. Some of them aggregate events into histograms, top left. Also, you can imagine voxelizing. It's like a 3D point cloud, right? And some of them only consider time windows or do other things like these kind of mixed density event stacks. However, the process for selecting such a representation is always the same. You need to first train a neural network on a given task, then optimize the hyperparameters with some validation score, and you have this loop which is very, very inefficient. So the question is, can we actually accelerate this process by looking at how much information is actually being lost in going from raw events to frame-based representations? And this is, I think, quite aligned with the goal here, because ideally we want to just eliminate this block, right? So if we let through more information, this should actually help. So instead, you could imagine now measuring the information loss between raw events and these dense representations with this thing called the Gromov-Wasserstein distance discrepancy. And what's nice about this setup is now it's actually much, much faster to compute this. And also it's network and task agnostic. So it's much more general than having to define a network and a task to actually evaluate your representation. So another thing that is amazing is that this information perfectly correlates with the performance of a neural network trained on this specific representation. Here we're showing a metric MAP. It's an object detection metric which tells you how well you can distinguish different classes and draw bounding boxes around them. And we can see that as the GWD reduces, the MAP always increases. And this is for different neural networks that we tried, different representations in text next to the dots, and also for different data sets and different tasks. And what's interesting is now by, okay, this doesn't work. There should be a star here. By now explicitly optimizing this information, we can find new representations which are even more efficient and even more powerful than the previous ones. So this, yeah.
So you keep the network architecture the same. You just optimize the hyperparameters that convert the raw event data to frames.
Yes.
And go to the right on this chart. Like the red ones become even.
So what I'm plotting here is different representations. So you saw before a picture of different. For each one of them, you can compute the information loss in generating them, and then you plot here what is the information loss, and also how well did my network perform when I trained with it.
The star should be like below time surface.
Exactly, the star should be here. Exactly, exactly. So we are further to the right and lower down. So this is actually good news, because now it means that we can just go beyond frames and just look at events in a sparse and kind of non-frame-like fashion. So let us review quickly a bit how events have been processed in this way, either as raw events. Here typically people use spiking neural networks. These are bio-inspired networks that are like a dynamical system, And in this dynamical system, you're inserting individual spikes, and then you have a decay over time. And then you can actually learn some learnable parameters in this network. However, since they're quite new, the learning techniques are approximate. Actually, spiking neural networks are not differentiable, so you need to rely on surrogate gradients to train them. And this means that many of the networks that exist nowadays actually underperform or only work on very simplified tasks. Another way to look at events is, as you've seen before now, as a 3D point cloud. So you could imagine using one of these models that have now appeared, like PointNet deep sets that process point clouds in a deep learning way. And they also are easily trained because they just use backpropagation. However, since we have a point cloud, we don't have a notion of how close events are. This is actually fixed with graph neural networks. So here, maybe I'll explain it a little bit. The points are the same points, but now we are connecting them via edges. And these edges are connected whenever the points are close enough. So now what we can actually do in this graph neural network is send information between points and thus learn local or global context on the events. So we actually solved this topology problem. And finally, there's also submanifold sparse convolutions. Maybe somebody has already worked with them, but they essentially treat events as a sparse grid and then only output sparsely the activations. So these two contenders on the right look very easy to train, but we have one problem. They still look at frames of events and then process these frames. So what we actually want is to have something that can process individual events as fast as possible. And so the question arises is, could we actually just convert these networks into asynchronous networks? Yes, we can. So here I'll show you a series of papers where we have taken existing sparse neural networks here on the left, trained on frames of events with backpropagation in a feed-forward way, and then converted these networks into asynchronous networks. So here what you're looking at on the right is now a sideways view of this set of events. And over time, we're now inserting new events into this window. And then what we want to do is we want to find out how do new events actually impact the output of the network, right? We want to have at the output a very high temporal resolution prediction from our network. And the way that you would do this naively is you would have to recompute your representation, recompute all of the activations of your network, get a new output. Next event, you do the same. And this is actually very, very inefficient. And for this reason, we actually consider only local computation. So you can imagine that to have the exact same equivalent output, you only have to touch certain activations in your network because each event only changes 1 pixel. And when you go through the network now, you can see that we essentially only have to update this expanding pyramid of green dots for each new event. And this is a substantial reduction in the computational complexity of these methods. So here I'll show you one example where we applied it to a graph neural network. Here we're again looking at events from the side. And imagine now you have a few layers that process them. Also there's a pooling layer there. And now imagine you get a new event. This new event is here. You see that this event is not connected to any of these nodes. And this actually means that in the next layer, we only have to look at a local neighborhood around this event and update these nodes. And you can see that this is propagated over the different layers. So how do these models now stack up against the original models that I showed you that process events as frames? You can see on the right the two state-of-the-art. One of them processes events in a recurrent fashion, one of them in a feed-forward fashion. And you see that they have very high MAP, but they're quite far to the right. So the amount of computation to incorporate a new event into the prediction is very high. That's what's on the x-axis. And now now I'll show you a series of works. The first one used submanifold sparse convolutions. applied this asynchronous formalism to it, and we could see that by adopting sparse convolutions, we could significantly move to the left, so reduce the computation by 2 orders of magnitude. But this method is still underperforming with respect to both feed-forward and recurrent networks. So for this reason, we transitioned to asynchronous graph neural networks, so what I showed you before. And in this case, we can actually reduce the computation much further, so almost 5,000 times, while reaching on par performance now with feed-forward networks. So now we can say that these models are highly asynchronous, very efficient, but they achieve exactly the same performance as a feed-forward model. You can see from this plot that there's still one goal to be reached. So there's these recurrent networks that we want to reach. And the question now arises, how can we actually close this gap? So looking closer at how recurrent models work, here I can give you an example. So remember, event cameras only see changes in the image. And when the camera is static, there's no changes. So a feed-forward model has only these events to operate on, and so it cannot see anything. It can only see maybe this person walking. Instead, recurrent models retain memory from previous time steps. And this memory is important to then grab and then reuse to also detect objects when we're actually not moving. And this means that recurrent models, they somehow have an internal representation which is what we term motion invariant. So when there's no motion, we still have this representation which we can grab to make predictions. So maybe the key to overcoming this problem is actually leveraging these motion invariant representations. So now let's talk about motion invariant representations. Sure, yeah.
Question before. So you're not using GPUs here, right? When you compute flops. Did I get it right?
Yes, we're using GPU. So flops is it's a computation metric. It doesn't concern. Yeah.
What I'm trying to make is that if you are going to pass like entire image or maybe entire graph,
yeah.
like in GPU, if you have the memory that will fit this entire thing, it will still be able to do all those nodes, process all nodes in parallel. So if you limit your computation to one node, you technically decrease your flops, but probably you don't decrease the time because everything would happen in parallel.
Exactly.
Anyway, right?
Yeah.
Being CPUs, it makes much more difference. That's what I'm
Yeah. So I think the main caveat here is, as you said, we are talking about computational complexity. We're not at the moment talking about runtime complexity, which also depends on the specific hardware that you're using. But I'll show you maybe some outlook for what kind of hardware can be used in the future. Yeah.
One more question. So once there is no change in the image frames, I see confidence values of cars. 0, 9, 6.
Yeah.
So did it change when there is no change in the image?
Let's see.
Yeah, okay.
Then I don't know. Let's see how it changed.
It wasn't now. It's 97. It's 98.
Yeah, it's
increasing. Okay.
That's interesting. Yeah, I think these confidence values are a bit to be taken with a grain of salt, because usually what we observed is that either it has full confidence or it doesn't even see anything. Okay. But this is, I think, maybe has more to do with how the network is trained exactly. Yeah. All right. So, okay, so now let's talk about motion invariant representations. So one motion invariant representation, which I haven't talked about yet, is our images. So when we have no motion, the image can still see something, right? So why don't we just use images and combine them with events to propagate the information? So here I'm showing you now a series of projects which have implemented this idea. We have a not motion invariant representation, which are the frames. We extract some corners from them, and then we track these corners over time with the events. Here on the right, you can see how this processing paradigm works. We are generating feature tracks, which are these green lines over time. And you can see that with the events, we can actually capture these high-speed motions, which I show on the left. By tracking the features in the blind time between frames, we also get a 2 times higher accuracy and a 3 times longer feature tracks than using only event-based methods. So meaning that if we don't have this motion invariant representation, we actually underperform significantly. This is actually confirms the this hypothesis from previous. Another application is event and image-based video frame interpolation. So imagine now you have a low frame rate video, you have events in between, and now the goal is to produce intermediate images so that we can have a high-speed video. And this is exactly the same idea. We have keyframes and we try to propagate now the information from these images with events to make a high-speed video. Here you see an output of this algorithm. We can capture this high-speed scenario, which we recorded with a gun, so shooting this bottle here. This is now the output of processing events and images together.
Is it correct?
Yeah.
How can you verify? You can have an extremely high-speed camera,
yeah,
very expensive, and compare.
This one is a qualitative video, but usually what you do is you have a high-speed video and then you remove images, and then you regenerate them and you see how well you regenerate. Yeah, that's how you usually evaluate these methods. Here I can show you also qualitatively. You can actually see how low the frame rate of the camera is. You have absolutely no detail in between these bubbles going up. And here on the right, you can actually see that the high temporal resolution of the events can actually capture all of these minute motions. So the main thing that I want to show in this slide is that that since we have events give a lot of information, and removing this information results in significant artifacts in purely image-based methods. So I'll just skip this slide. Here I'll show you a couple of more examples of what happens if you remove events. On the right, you have this typical rotational motion. And frame-based methods don't know that it's rotating because they don't have this information. And it results in these cutoff corners here. With events, you have the full information. You have this high temporal resolution data stream. It can actually generate very high fidelity, high-speed video in this way. Here's another interesting example. We recorded this fountain going at exactly the frame rate where we get visual aliasing. So you take one image, the next image, the wave moved exactly one period down, and now the algorithm on the right doesn't know anymore whether the wave is going up or down. And that's why you see this kind of strange motion, right? And with events, you actually capture the full data, so you can actually recover the high-speed video perfectly. Well, yeah, with very high fidelity. Okay, so here we are still treating events as dense frames. So how can we actually now leverage the insight of using images and events to do at the same time efficient but also robust processing? So this is what we tried in this work, where we basically combined the asynchronous neural network that I presented previously with the dense CNN. And you can see that now we are using the CNN on the images to detect objects, and then we use the graph neural network to propagate the detection forward in time in this asynchronous way. And you can see that by doing this, we can now actually overcome the perceptual latency of frame-based cameras. So let me show you an example of this. So here we see a pedestrian running onto the street. And we can see that with the few events and the image that is provided, we can already detect the pedestrian reliably. Whereas the frame-based, the one that relies on the frames, still needs to wait maybe for additional frames to see this pedestrian. And this means that we can actually react much faster than if we, for example, had a purely frame-based method to detect pedestrians. Here I'll show you another example. With the events, we can actually detect this car coming on from outside of the tunnel, which is overexposed.
Yeah, because of dynamic range.
Exactly, the dynamic range. Here we have another example where the car is coming out of the tunnel. It's too dark, so we cannot see it yet with the frame-based camera. And here we have another example where we'll discover that there's a pedestrian here on the right trying to cross the street. So we are really leveraging now the high-speed information provided by the events, but also the high dynamic range to have a higher confidence in low light. Here's an example where we see, maybe you can see that there's well, in this light it's quite difficult. There should be kind of a shoe on this right image, but the detector couldn't detect the pedestrian in this case. So looking at this, looking at how good this method now actually performs, let's look at how the detection quality changes over time when we go into the blind time between frames. This is what I visualized here. So at time 0, we get an image, and then over time, until 50 milliseconds, we only see events. And now you see that at this time where we have the image, we have a certain quality of detection, and then using events, we can propagate these detections over time. So we maintain a high performance in terms of object detection. Now, instead, if we only look at images and we look at how the object detection labels move over time, so as we are moving over time, our data becomes more and more outdated. And this means that we actually lose in performance. I hope that this point is clear. That's why the object detection performance actually reduces by over 11 MAP. And what this actually means is that depending on the frame rate of our camera, we have a different worst case performance of our algorithm. So if we have, for example, a 20 Hertz camera, which has 50 milliseconds in between, we could, for example, just miss the object and then have a 50 millisecond time where we don't see anything, right? And this actually means that we are actually at this point. And if we plot this point for different frame rates, we can see that the performance now follows a curve. And it means that if we have higher bandwidth, which means higher frame rate, the highest frame rate gets the highest performance because it can capture the object as fast as possible. But if we have a lower bandwidth, we have a lower frame rate, we could actually be missing the object, and that's why it goes down in this direction. So the reason why I show now bandwidth instead of latency is because we can plot our event plus image hybrid setup into this same plot and figure out how much actually are we improving on frame-based methods if we consider the same bandwidth. And this plot actually suggests that a combination of 20 FPS images plus events behaves similarly to a 45 FPS camera in terms of bandwidth, but has the latency of a 5000 FPS camera. And this means that we can actually improve the worst case by a significant margin. So looking back at these algorithms, we can see that this algorithm somehow reconciles both the robustness and the efficiency of these approaches, but is still kind of far away from biological vision systems. So we still have some work in front of us. Moreover, what we realize is now we're only talking about the eyes. We're not talking about the body of the biological system. So the question is, can we actually use these algorithms now to control robots? So I'll give you a little outlook on a few projects that I've worked on which do this. So here there's one project which does event-based obstacle avoidance. And the way that it works is here you see an image-based camera seeing a blurry ball, and here you see a data structure which is derived from the events, which we call the mean timestamp image. And by thresholding this image, we can actually detect moving objects with a very low latency, so with a 3 millisecond latency. Sorry, even lower latency. So 3 millisecond is the perception to action latency. So actually it's even faster than that. And then it uses these detections to execute an evasion maneuver to evade the object. This idea was also implemented. So instead of now evading these objects, we could actually think about catching these objects. So then this idea was also implemented on a quadruped. Here, the animal. This is a lab at ETH which developed these red robots. And here you can see that our algorithm tries to catch objects at up to 15 meters per second speed by tilting to the side. Here I'll give you a little bit of an overview of how this is exactly trained. So you can visualize the setup here. We have some point where we expect the object to enter the field of view, and then we use a policy to take this point and the previous action commands to control the robot. And in this way, we are completely agnostic to vision because it's a purely geometric problem. So we can just simulate this and train it in a massively parallel fashion in RL. And then once we deploy it then in the real world, we actually get this thing from the event camera. So we can use these detections to find the point where it intersects this plane. So I'm already at the conclusions. So some conclusions that we've made now is that, first of all, information loss is important when we talk about frame-based representations, and it can actually deteriorate learning if we don't take it into account. Another point is that we saw that we can actually have easily trainable asynchronous models which are derived from standard models, and they are highly efficient and only use local updates to achieve this efficiency. The third point that we learned is that events alone are not enough to perform robustly. What we also need is a motion invariant representation. In our case, we saw that images are actually a very good candidate in this case. And we can then use this image information together with events to propagate information into the blind time between them. And this means that we can actually use images and augment them with events to reduce their latency. Finally, we saw that we can apply then these algorithms to agile object catching or dodging on robotic platforms. So yeah, with that, thanks for your attention, and I'm open for any questions that you may have.
How affordable is event cameras right now? Is it easy to start? Everyone had this question.
Yeah, so event cameras are still not as affordable. They have a 20%, oh no, this was last week. No, this week they have a 20% discount, but it's a discount from 4,000 euros, so it's still quite expensive. But they're actually, I talked to the manufacturer and they said that they will come out with a 30 euro event camera either this year or maybe beginning of next year. So yeah, let's see. That, I think that would be very nice. Yeah.
30, you said?
30, yeah. Yeah.
Do you use some custom hardware inside such cameras? Because usually hardware designed to work with matrices, not with custom events.
Yeah.
Do you use some custom CPU? Do you use something like this?
So there's some custom hardware that people sometimes use to process these events. These go under the name neuromorphic hardware, and they try to emulate how the brain works. So we have now the eye and then the brain. The brain has localized memory. So this hardware has this localized memory, and it communicates over spikes. So this means that it's kind of low power, and usually people use this kind of hardware to accelerate event-based perception. Some chips, for example, include this spec chip in particular, but there's also Intel Loihi, and there's Loihi 1, 2, and then there's a I forget the name. There's like a larger chip that combines several of them. Yeah, these are all available to do this processing.
Can you please talk a little about the future of this technology, the challenge that you are faced with?
Yeah. So one of the challenges is really this hardware and software co-design. So one of the main promises of event cameras, as you can see, is that they are efficient. But if you run them on a GPU, they're not efficient anymore. And the GPU is kind of the dominating computing paradigm now in machine learning. So we need to kind of work together with these hardware manufacturers to actually find something that is a killer application that shows really the efficiency gains of these events. This is one challenge, and at the moment these chips are quite small, so we cannot make an event-based, let's say, ChatGPT and then run it on these chips because they're too small. So we can actually only do small applications like face recognition or gesture recognition on these chips natively. That's one challenge. And I think another challenge is there's this promise of high dynamic range of the event camera, and currently there's a little bit of a discussion whether now this is interesting for automotive applications. But in automotive, they have, first of all, they don't care about efficiency, and second thing is they don't care. They have very good automotive cameras that can see with very high dynamic range. So actually, they're being kind of outcompeted by these cameras at this point. So finding this niche somehow where the event camera can be used. Although in this scenario, actually, they've noticed that eye tracking is very interesting with event cameras. They can, for example, monitor how drowsy or how awake a driver is with event cameras by not filming the street, but actually the driver. And additional challenges are finding new applications. So this kind of research, it's like I have a hammer and but I want to find out how I can use it. So we are always trying to find new applications where we can actually use these advantages, and where existing solutions are actually not working as well.
My question about disadvantages. So
yes.
As I understood, disadvantages not see static objects.
Yes.
Also hard to work with GPU, and maybe another disadvantages that I didn't mention for this technology. I mean.
So this technology until last year, it was using still quite old CMOS technology. So the sensor quality, like the signal to noise ratio, was not excellent. Now they've changed in the last year. It's gotten better. But so one disadvantage is they're still relatively low resolution. So we have HD cameras, but we don't have full HD 4 megapixel event cameras yet. That's one thing. Then another disadvantage. Well, that's the one that I can think of right now. Maybe I will think. I'll come up with more later. Yeah.
I sort of missed this part. When you use events to build a model, do you just model the movement, or you also classify the object?
Also classify. Yeah.
I have a question that is more implementation specific.
Yeah.
I understood that when you obtain representations, use some kind of algorithm like SIFT or KFT. My question is, as a pre-processing step, do you also align, do you do feature matching as well before feeding it to GNN, or do you let the neural network figure out the relations from frame to frame?
No, we don't do that at the moment, but it sounds interesting.
Do you need any special libraries to work with event cameras, or OpenCV is enough? It works? I don't know.
Well, as soon as you have an image, you can use OpenCV. Converting events into images, there's some libraries. It's pretty straightforward to set up and to work with. But working with raw events, like doing crazy graph operations, stuff like that, I think is not that developed. Like the ecosystem is not that large. There's also some competing companies that they have their own packages. I think the one that is most developed is a company called Prophecy. They have like a whole SDK with machine learning tools and everything that you could try out. Yeah. I think to learn most about event cameras, you can go under. You can visit these links at the end. So here, if you are interested, you can go to these slides and to these links, and you can find papers and information. Mm-hmm.
So I want to understand how these event cameras behave if they themselves are moving.
Yeah.
Because it's kind of, I can imagine if it's static and the rest of the world is moving, you capture only those that are, but if you are moving, then almost everything is moving. So.
Yeah. So the main thing that you observe with event cameras are edges then, because actually, maybe I can show you this example.
You showed this avoidance thing, right? That
Yes.
That in that case, it is moving by itself, right? So
Yes, but there's also a thresholding step. So there's so in this algorithm that I showed at the end, you're segmenting out objects which are generating events due to ego motion and objects that are moving independently. So there's another processing step which I didn't go into too much detail about.
But it's doable, it's not a problem.
But this can be done, yeah, exactly. So there's an efficient algorithm to remove actually non-moving objects. Yeah.
These cameras be used to perform spatial mapping, maybe with depth cameras combined?
Spatial. So.
I mean, like SLAM.
Yeah. So there's some algorithms that use event cameras for SLAM. There's also some impressive videos. Maybe you can check them under these links, where my colleague was like swinging the event camera like a lasso, and you could actually reconstruct the full trajectory from it. And the reason is because they don't have motion blur. Motion blur is the biggest issue when you're swinging it like that, and you can actually get. But usually they're combined with IMUs. IMU is very important, and sometimes even images. So then you have three sensors essentially. And the event camera can take over when the image camera is not good, and then when you're static, the image camera can take over.
Okay, but what if, for example, they use collider that estimates this distance?
I think not so many works have used LiDAR with event cameras.
Okay.
Yeah. Something to consider is also the LiDAR sends out infrared radiation, and this infrared is actually detected by the event camera. So you need to put an infrared filter in front of the event camera, otherwise you see the rotation actually in the events. But it's no problem, you just need to think, you have to know that this exists.
What are the most popular commercial applications of these cameras in general?
Yeah, so the most popular ones are, I think, smartphone computational photography for smartphone technology. So one of them is, for example, deblurring of images, because you have really the high temporal resolution. You can deblur images. This makes it cool to take pictures maybe at night, where you usually have problems with motion blur, and saturation at the same time. Another thing is, for example, IoT devices that, like closed circuit TV, for example, that you plug it into the wall, and most of the times you don't record data. You can now extend your battery life of that device by orders of magnitude, because you're not always collecting data. You are only collecting when something moves. And thirdly, I think high-speed videography is also quite interesting. Like they use it, for example, for vibration detection in machines to see where things are breaking, for high-speed object counting, for sure you could also do some kind of sports application where you can observe how someone is swinging the golf club, something like. So these are kind of the three main things that I.
Thank you. Do you know any work that tries to apply transformers for this kind of event data? Like imagine every new pixel that has changed is one token. Maybe you have some embedding that shows where this pixel was and what was the intensity change.
No, actually, this is still open, and I think it's interesting, especially because the events, there's usually it's like millions of events. So far, the transformer technology was not so good that we could not process all of the events at once. But I mean, nowadays we have better transformers.
You can maybe cluster.
Yeah, you could reduce the data somehow. So in fact, actually, the recurrent model that I showed you, it uses this idea, but it's more of a vision transformer on event frames. It generates, and it's like so it looks at patches of events.
What kind of hardware is required to make that dog behave so quickly, like these agile movements, catching the ball?
Yeah.
What is does the computer fit inside of that dog, or is it connected to something external that is computing?
This is all onboard perception and control. So it uses an NVIDIA Jetson.
Like the Nano.
Yes, and then it does a lot of GPU optimizations to run in real time. So it runs at roughly 10 hertz, 100 hertz, 10 milliseconds latency, but it's not yet fully optimized. I think could be optimized further.
And that is the total latency between the ball swinging and the perception,
exactly.
The command like catch it.
Yeah. The reason is because the reason why it's higher, so the drone has 3 milliseconds, the dog has 10 milliseconds. The reason why it's higher for the dog is because we're actually online estimating the trajectory of the ball, and so we need multiple detections. Whereas the drone only sees the ball and then does an evasive maneuver. It knows exactly, okay, I just moved perpendicular to the detection. So that's why that's actually the main reason why it's still, not optimal. Yeah.
Nice.
Yeah.
Actually, event-based approach looks very general and biology inspired. Are you aware of any applications outside of vision domain with any other modalities?
With other modalities, where you have event-based,
any type of data, actually. Even streaming data.
Yeah. So, if you're really interested, you can look at the works of Toby Delbruck. So now in his lab, he's developing, for example, the dynamic audio sensor. It's a sensor that translates the pressure wave which enters your ear into an event stream, and then it also has these kind of efficiency properties that an event camera has. Well, you could argue that avalanche diode SPADs, so single photon avalanche diodes, are an instance of event camera. They're used for very high precision 3D reconstruction and low light imaging. Those are the two that I can think of. Yeah.
I don't remember if anybody already asked this question, but I'm interested. Can we compare the latency of these event-based cameras, not with other cameras, but with LiDAR, for example?
Yeah.
So it's low, or it's equal, or they have a high latency?
So LiDARs, they're usually spinning. Either you have the spinning LiDAR, so there you have, if I remember correctly, it was like 16 milliseconds. We used once a LiDAR that had 16 milliseconds rotation time, so you're waiting for, so you had like 60 hertz. But then the LiDAR also records while it's rotating, so it can actually give you already some points or some lines before it finished doing all of the lines. So you could have, in our case, let's say, you can reduce this number by a significant margin. So I think if you look at only like the individual lines, it's actually similar to event camera probably. But the main difference is that you're actively imaging, and this is actually, and in the event camera it's passive, like you only transmit information where it's relevant, whereas the LiDAR, it just always records data, and sometimes it's irrelevant, sometimes it's relevant. So you still could have some high latency if you, for example, if your object is maybe all the way down in the bottom, but you missed it, you still need to wait until it re-scans all of the lines. Yeah.
Thank you.
One more question. There was a paper from your group in Nature recently, right? The process from racing stuff. Does it use event cameras?
No, actually it just uses standard cameras. So at this point we haven't used it for drone racing because they are still very, very expensive. And during this project they crashed a lot of drones, so we don't have the money to buy that many event cameras, unfortunately. Yeah.
When the $30 will be ready?
Probably, yeah. Then. Okay. All right. Thanks, everyone.
Thank you.